What is a propeller? A propeller is all about that thrust, and it's everywhere. For example, propellers are found on helicopters, on ships, on drones, and subsonically, most importantly, on airplanes. A propeller can also be seen as a pair of rotating wings. But how? Consider the following. Here we have a pair of rotating wings turning around an axis of rotation. But how does this translate into what we know as thrust? It's all about that pressure. On the rear face of the propeller, we have a region of high pressure, while on the front face of the propeller, we have a region known as the low pressure region. This creates a pressure differential which causes thrust. From a graphical point of view, we can see the pressure gradient. Whoa, but wait, hang on. How does power come into play? We have some power source that turns the propeller that gives us thrust. But the question is, what is this power source? This is an electric source that supplies the motor with power, which produces a torque that is transmitted to the prop, creating what we know as a pressure differential. But hey, a pressure differential. Eureka! That means we have thrust! Ta-da!
So how can we design propellers and analyze them? One way to do that is by using blade element theory. Blade element theory analyzes the performance of propellers by taking 2D sections at different points on the propeller and analyzing the section independently. By doing that, we end up with an airfoil section of chord length C, which corresponds to the chord length of the propeller at this point. This airfoil is subjected to the incoming flow velocity VA and the radial flow component omega r, where omega is the rotational speed in radians per second. The resultant flow VR acts at an incident angle beta. The angle between the airfoil chord and the resultant velocity direction is the angle of attack alpha. The pitch angle or the blade angle is the angle between the rotational plane and the chord, which is the sum of the angle of attack alpha and angle of incidence beta. The elemental lift dl and elemental drag dd of that blade element acts perpendicular and parallel to the resultant velocity direction. In order to compute the dt, the elemental thrust, and the elemental torque of this blade element, we need to take the elemental lift and drag components in the rotational plane direction and the direction perpendicular to it. When the propeller is immersed in fluid, an axial and a radial velocity is induced at the propeller. This changes the effective angle of incidence, which must be accounted for to get accurate results for the thrust and torque. Now we are going to give you an insight on the design process.
For our project, we had to design the propeller considering both the efficiency and static requirements. We first tackled the efficiency calculations to obtain the geometry of the blade and apply it to the static thrust case. First, we set our incoming velocity to 5 meters per second and RPM to 9,000, as set by the conditions. The maximum allowable diameter for our project, 130 millimeters, was chosen as actuator disk theory shows that maximizing area also maximizes efficiency. Next, we discretized the blade at 4 points. For each radius, we choose a NACA airfoil number based on literature and a chord length, but this will change through iterations to get an elliptical distribution. Next, we must find the efficiency using the following blade element moment theory equations. Next, we assume that at each radius element, the efficiency is constant. As you can see, we want to cancel out the radial term in the numerator and the denominator of the efficiency equation. From that, we can get the induced beta plus gamma term. Next, we use X-foil to find the lift coefficient, lift or drag ratio, and angle of attack at peak efficiency, which is when the CL over CD versus alpha curve peaks. With all this information, we can now get the gamma value, the beta I value, and even the pitch angle. We have now everything we need to compute the elemental thrust at each radius. Summing up all the thrust values yields the total thrust of the blade at maximum efficiency, as you can see. Or so we thought. To account for the static thrust requirements, we use the same procedure, but recognize that since U infinity equals 0, beta equals 0, thus beta I equals 0, and the angle of attack equals the pitch, which we can get from the geometry of part 1. We can then compute again the total static thrust, which in our case gave us 0.34 Newton. An overestimate to account for manufacturing inaccuracies and tip losses. Now that we have our dimension, we can create our CAD to send to 3D printing.
The first step taken to realize this insightful project was to create a 3D CAD model which we 3D printed using an SLA printer.
2,000 years later.
Ka-ching! For the post-processing of our blade, we first had to sand away the rough edges to smoothen the imperfections. To stiffen the blade, we first used resin. Pour the resin into the cup and stir well. Coat the blade evenly, this provides a much needed strength. Allow 24 hours for drying, this hardens the resin which will support our prop during the heat of the battle. Bravo! Bravo!
So after doing the wind tunnel test, we got an experimental efficiency of about 15% at the efficiency test conditions, while we expected about 80% from our spreadsheet analysis, and J-Blade gave us about 10%. One of the major errors we got during our calculation was due to analyzing our propeller as if the two blades were attached root to root without taking into account the hub in the center, which would reduce our overall thrust generated. Another main source of error in our analysis comes from some of the limitations of blade element momentum theory. And one of them is that it doesn't take into account tip losses or tip vortices. Another one is the effect of interference at the hub, which is the second one. And the third part is about streamwise flow components, all of which reduce overall performance. And finally, the fourth component comes from the fact that the weight coming off of one blade affects the incoming flow on the other blade, so the blades are not independent in real life. Some of the ways to remedy this situation is by analyzing using numerical vortice lattice method solvers for propellers like J-Blade, but those still don't take into account the spanwise flow, which is number 3. An even more accurate way of analyzing our propellers would be full-blown CFD, which takes into account even more effects that we don't fully understand at this point. So another issue we discovered during wind tunnel testing was a structural one, where our propeller would oscillate and deflect way too much at the tips. This was because it was way too thin and is a result of our airfoil selection. The oscillation created a lot of extra drag and dropped our efficiency way below what we were expecting, which is another explanation for why we weren't getting that. Ways to fix this issue would have been to use truncated airfoils, which would have allowed us to avoid the chipping at the trailing edge. And another way to increase the stiffness of the airfoil would have been to use thicker airfoils. Hopefully the topics we discuss in this video serve as a good aid for future propeller design.
One must realize there is no such thing as a perfect design, just some designs are useful. It is our responsibility as engineers to push the boundaries, take risks, live on the trailing edge.